Since we are one student down in my first block class, there's various theories. Maybe this person didn't get their homework done, maybe they just decided to skip, maybe they've been abducted by aliens, maybe they're at the dentist. I don't know. But because of this person, I've got to record this lecture. Okay, so let's chit chat about the lab. So here's the main idea. When you were looking at, let's say for example, that velocity time graph, okay, and it goes ding, 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 right? And here's 0 meters per second. And here's your thought process that you want to go through. And you remember this in terms of what's going to happen today in the lab. Bless you. Is that basically every idea on this lab is brought to you the idea that force applied plus force opposing equals force net. Literally, that is the basic idea of everything that happens on this lab. So, and this is important once you get to questions 5 and 6 on that back side. Of those three forces, force net, force applied, force opposing, which one of those three is the only one that is equal to mass times acceleration?
Force net.
Force net, that's it. That is the only one that equals mass times acceleration. So this is where this turns into a logic. Okay, here's a velocity time graph. What does the slope of a velocity time graph give you?
Acceleration.
Acceleration. So you start off and you have some positive acceleration, which means what has to be the sign of your net force? Positive. Because mass can never be a negative number. So what that means is your net force is always going to have the same sign as your acceleration is. Okay, there's no exceptions to that rule. That's it, boom, nothing else. So then you're going to switch to having a negative acceleration. Well, if you look at this in terms of, since this is your vertical motion, and you have negative 8350 as your opposing force, if you want to have a positive acceleration, what's the only way that can happen in terms of the relative value of your applied force versus your opposing force?
It's got to be. It's got to be bigger.
Yeah, your applied force has to be bigger than your opposing force, okay? Because you always have the vertical mafia that you have to pay off, okay? So even if you don't pay anything, you completely shut off the engines, you still have that negative value of negative 8350, which is going to create a negative acceleration. So the only way that you can alter the acceleration is, and if you look at what you control in the program, what you controlled was the value of that applied force. So this is a domino. Oh, if I change my applied force, that changes my net force. If I change my net force, that changes my acceleration. Okay, so that's kind of the thought process that you want to go through. On 5 and 6, first off, both of those answers should be positive values. Okay? If you have any negative answers on 5 and 6, what you're telling me is that you've taken the limb, you've flipped it over, and you're accelerating downward. Okay? Cool. Probably not what NASA wants you to do. So, and you remember this in terms of the lab today. So you want to get a vertical acceleration of negative 1.1. So you could do mass times acceleration. You still know the mass of the ship is 5,000 kilograms. You know your acceleration. So obviously when you multiply those two numbers together, what does that get you?
No.
That gets you your net force. Is that what you're ultimately after?
No.
What are you after?
Force applied.
You're after the force applied. Now think this through. There's a couple of ways you can do this. One is mathematically. Okay? Oh, okay. That's negative 8350. Okay? You always have that working against you vertically. You have your net force, which you just found. Boom, there you go. Solve for your applied force. Now, here's what I want you to think through. Since you want a negative net force, is your applied force going to be bigger or smaller than 8350?
Bigger.
Much.
Way smaller. I lied.
I thought you said negative, so.
You want a negative net force.
Smaller.
Up.
So your applied force has to be,
Bigger. Bigger. Smaller.
Small.
Bigger.
Smaller.
Exactly the same.
Applied.
No,
Exactly
that
the same would be zero.
Final answer, bigger.
Applied.
okay,
No, smaller.
Why does that have to be small?
Gavin, let's say you think the applied force is 9,0 newtons.
Okay.
If I take 9,000 and add that to negative 8350, what's the sign of my answer gonna be?
Positive.
Which is gonna create a positive acceleration. On number 5, what kind of, what's the sign of the
I
acceleration
lied
on
to
number
you.
5?
Yeah, I full lied to you. So it's gotta be smaller.
Yeah,
Okay. I didn't know what the question was.
but yet you felt very confident in that answer.
I mean, it was 50-50.
Yeah, no, it wasn't.
Always gotta go for 'em.
Now, here's the story on number 5 and 6. Here's how you can check that your answer is right. Take your answer to number 5. Let's say you think it's 4,000, which it isn't, but let's just say. Take 4,000 and add that to negative 8350, find your net force. Divide that by the mass, see if you get an acceleration of negative 1.1 meters per second squared.
Let's just do that.
If you did, odds are you did it right. If you don't get that acceleration, I promise you, it's wrong. Okay?
No bueno.
So, make sure on that velocity time graph that you have indicated clearly if the net force is positive or negative. I don't care if you do plus minus, if you shade it, make one color positive, the other color negative. If you want to like draw vertical lines to differentiate it and go, hey, here's what's happened in each one. I don't care, okay? But just make sure that I can clearly see what is happening in each segment, okay? Make sure that I can clearly see that. Okay, any questions on that lab? Go once, go twice.
Wait, how do we check our answer on 5? I'm sorry. I was confused. I got my calculator out. Forgot.
Take your answer to number 5, use that as your applied force.
Uh-huh.
Add your force opposing, get your net force. Divide that by the mass, see if you get that acceleration of negative 1.1.
Oh my gosh, I got that.
Then that's probably right.
I'm way in.
That's 1.
No, that's more than one.
Oh, is that 2?
Some like 3. If we're
3.
counting, like, all
Okay, you're
uses
at
of
the
Spanish.
general consensus, you're at the 3.
I've only heard one.
If we're
Same.
counting like all uses of Spanish, that's number 3.
It's specifically the muy bien.
No, it's specifically the BN.
The end is just 2?
No, BN is 3.
Okay, you're up to 3 on
But
the
it's like, it's just the word BN.
Okay,
Just
So I'd say muy.
so we're at 3.
Moi.
That's,
Boy.
that's annoying too. Okay, so get that handed in.
We'll see if Vanessa comes with it, I doubt she will. Oh. Ooh, what'd you bring? Snacks?
I think those are weights.
What'd you say you wanted?
My paper was off.
Oh, okay. I thought it was.
Okay, so the lab will start today, I'll finish up tomorrow. Oddly enough, is brought to you by the idea that force net equals force applied plus force opposing, okay? Okay, so if you notice, this is one of the big equations that exists in all of physics. So, the first thing we're gonna do is we're gonna deal with vertical motion, okay? So, typically, these are known as elevator problems, because it's usually either like a helicopter or an elevator. So that's what we call them, elevator problems. So, you kind of intuitively already understand this process. So, let's say that in this bag, I've got 3 1-kilogram masses, okay? So, each one roughly weighs 10 newtons, okay? 1 times 9.8 is 9.8, let's round it up to 10, okay? So, if I want to lift this up, okay, at a minimum, how much, let's say this weighs 30 newtons. At a minimum, how much force applied do I have to have?
31.
Yeah, 31, 30.2, 30.3. It just has to be greater than that, right? Because I want a positive net force, okay? So if I do this, I can lift it up, I can make them accelerate, right? Cool. So if you look at this in terms of forces, when it began to accelerate, right? I had a positive net force. So the only way that happens, if that applied force going up has to be a little bit bigger than the opposing force going down, right? It's the only way it's going to happen. So if I lift this up slowly, notice that the bag stays intact. So fundamentally what's happening, if you look at the bottom of that plastic bag, plastic bag is applying upward force to overcome the gravitational force. So this is a set of equal and opposite forces. Set of equal and opposite forces occur also when I lift up on the handles, right? Okay, I lift up on the handles go down on me. So if I lift it up slowly, everything stays intact, right? But if I do the same thing, but I lift it up quickly, I rip out the bottom of the bag.
Why to do that?
I know. So when I tried to lift it up very quickly, what happened to the value of my applied force?
It went way up.
Oh, it went way up, right?
Oh! Oh. I get it now.
What?
No,
What?
I don't get it,
Yeah.
but I get it now.
No, what do you
Did
get?
the bag rip?
I
I
know
don't
what
think
happened.
he's got this far yet, Gavin. You don't know what happened.
Well, we're gonna see. I'll let you know.
Okay. So did the bag try to apply an upward force to the weights?
Yeah.
Yes.
Yes.
That means the weights put a force on the bag down.
They did.
That's what I was thinking. That's what I was thinking.
So what happened is that the force from the bottom of the bag, in terms of that plastic being held together, exceeded the strength of the plastic bag itself. And so basically it tore it apart.
I bet you that's
Ask her for her homework right before she walks in.
Yes.
She needs it to watch.
Hello?
Okay.
Hey.
Did you have any cavities?
That's tomorrow.
Oh, so she was
Oh,
just
so she
skipping
did
today?
just skip.
Well, I thought my appointment was today because my mom told me it was today, but my dad said it's tomorrow. And I don't know.
Wow.
Okay,
She
anyway.
skipped.
Thank you.
Yeah.
So, what happened is that the bag has like a braking point. And when we try to accelerate that very quickly, big acceleration requires more force. So basically the plastic bag was incapable of providing that amount of force. But here's the point of the story, is that if you want something to accelerate upward, your applied force has to be bigger than the gravitational force acting downward. But there's a limit to what anything can do, whether that's a cable. So let's say, for example, you use a string. Okay, cool. So the string also has like a breaking point. And if I exceed the force that's exerted on that string, it breaks. So here's what I want you to imagine. You walk into an elevator. It's on the ground floor, and you walk in, and this is going to sound weird, but it's in the name of science, and you're wearing a trench coat, okay? Which sounds weird. It gets weirder. You're also walking in carrying a bathroom scale, okay? So you're wearing a trench coat, and you're wearing and you're carrying a bathroom scale. And you walk in, and you put that scale down, and you stand on it, wearing your trench coat, and you look down, and for the sake of argument, we're going to use this pounds because that's something you all can relate to. And you look down, and the scale is reading 150 pounds. Okay, you're not moving. Okay, you just walk in, put the scale down, boom, it's showing 150 pounds. Now, keeping in mind what we just did, You want to go up to the 4th floor. Okay? You want to go up to the 4th floor. What's going to happen to reading on that scale when you begin to accelerate upward? Is it going to stay at 150? Is it going to go above 150? Or is it going to be below 150?
It's gonna go above 150.
Stay at one.
It's gonna go above it.
So some say it's going to stay at 150. Some say it's going to go above 150.
That's what's gonna happen.
Why?
Because when you go up, the elevator is putting force on you, so you put force back on the elevator, and you're putting force on the scale, and that makes the pounds go up.
Okay. Well, look at it this way. When you just walk in and you're just standing there, you can have your force applied and your force opposing. If you just walk in, boom, you're not accelerating. What's the value of your net force?
0.
0, which means your applied force from the scale is balancing out the opposing force of gravity. True?
See,
Yeah.
Now, if you want to accelerate upward, what has to happen to your applied force relative to your opposing force?
It has to be greater than
It has to be greater than,
Yeah.
okay?
Yeah.
So you are going to be accelerated upwards,
Yeah.
okay? So the bottom of the elevator is going to force you to accelerate upwards. So if you stay at exactly 150 pounds and both stay at exactly 150, you can't accelerate upwards because the forces are always going to add up to equal to 0. So if you're going to accelerate upward, and this is what the scale is measuring, that scale is measuring that value of that applied force. So the only way you can accelerate upward is if the force acting on you from the scale and the elevator floor is bigger than 150. So if you were to look at a velocity time graph, you're going to accelerate upward, right? The velocity time graph is going to go to 0 to some value. Maybe that's 5 meters per second, whatever that is. Now, eventually, what's going to happen to that velocity time graph?
Stop.
It's going to level off, right? Because you're going to move at a constant velocity in between floors. You're not going to accelerate the entire time, okay? So while you're accelerating, the force applied is going to be greater than your, and you're going to feel heavy, okay? If you've ever been in an elevator and you start it, like, you kind of feel like your stomach is like, because your stomach has mass. It has inertia. It wants to remain at rest. So you're being accelerated, and your stomach wants to lag behind, okay? Kind of feel that. So you're accelerating when that velocity time graph is sloping up. Once you reach the constant velocity in between floors, what's going to be the value of your net force?
0.
0. So now you're going to be back to reading 150, okay? Because your applied force is going to balance out that opposing force. Eventually, what are you going to have to do?
Slow down.
Slow down and stop, right? So at that point, if you're defining up as being a positive value, what's going to be the sign of your acceleration?
Negative.
Negative. So what's the only way that I can have a negative acceleration? Or, well, bigger idea.
Negative force.
Negative net force,
Net
right?
force,
Yeah.
So if you look at force applied plus force opposing equals some net force. This is going to be some negative number. So if I want to have a negative net force, what do you know about your applied force relative to your opposing force?
It has to be smaller.
It has to be smaller. It doesn't have to be negative. It just has to be smaller. So if I have a smaller positive applied force with a bigger negative net force, all that's going to happen is this: I'm going to slow down. Okay? So I'm still going up, and at that point, the reading on the scale here is going to be less than 150 pounds because of the fact that your body has mass. It has inertia. It wants to continue going up. So basically what's happening is the elevator floor is slowing out from underneath you. Now, you get up there, you stop, okay, I need to go back down to the basement. So now you're going to start off at rest, but then you're going to have a negative acceleration. So on the way down, when you start to move, your velocity time graph needs to go from 0 to some negative velocity. Are you going to accelerate?
Yes.
Yes. So is the applied force going up bigger or smaller than the opposing force acting downward? Smaller, because that's the only way I can have a negative acceleration. So on the way down, it's like the elevator is accelerating up from underneath you. Then you're going to move at a constant velocity again. Now you need to stop at the ground floor. What needs to be the sign of your acceleration?
Positive.
Positive. So now when you start to stop, when you get down to the bottom, what do you know about your applied force? It has to be
Greater.
bigger than your,
Opposing.
and that's why you're like, oh, right? Because now your stomach wants to keep moving. Got that? Okay, so here's what you're going to do in terms of lab. You're going to take a Newton scale like this. Now, you don't have to use a string, I am, just so that you get a little bit better idea of the visual. So I'm just going to tie a loop on each end. And get this section going. So we got this, okay? So we're going to turn it on. Turn it on. There you go. Okay, so I'm gonna hold it up like this, remember to re-zero it. So what you're gonna do is you're gonna take a 500 gram mass and you're going to act like the elevator cable. So you're gonna have this thing at rest and then you're going to accelerate it upward, okay? Now, here's the $1 million question. You have to get this idea right or everything in this lab is going to go south. What are you measuring?
Newtons.
Are you measuring the applied force, the opposing force, or the net force?
Give me a second.
Opposing.
Force, because of gravity.
Applied. Nope.
It's
Applied.
opposing.
Nope. The folk.
How many vote that I'm measuring the applied force when I'm reading this number?
I'll be different.
Really?
Good idea.
Yeah, really wrong.
You want to be different or not? You don't want to be different.
I know.
How many vote that I'm measuring the opposing force? How many vote that I'm measuring the net force?
Wait, what do you vote for?
I'll tell you in a second.
Oh, yeah.
You would have been smart to stick with the applied force.
Oh,
'Cause
dang.
that's what it's measuring.
Hey, you.
Because
you
what's
forced me out of my
creating
answer.
the opposing force?
Gravity.
Gravity. So you're measuring the applied force it takes to balance out the opposing force of gravity. Now, this reading is like 4.9. How do I know that this is not the net force? Right now, how do I know this is not the net force?
It's not accelerating, so then.
Yes, if this was measuring my net force, right now, if I was measuring the net force, what would it be reading?
0.
0, okay? It's reading like 4.9. So why is it reading 4.9? What is a point, if you take 0.5 kilograms times 9.8, what do you get?
4.9.
4.9. So this is reading 4.9 newtons because this is my applied force going up, if you define up as positive, which we're going to. So I have an upward applied force of 4.9. I got a downward force of, Vanessa, quit bouncing that ball, of negative 4.9. I add those two together right now, what do I get?
0.
0. Okay, this is the only way that these add up to equal to 0. So here's what you're going to do. You're going to accelerate it upward. You're going to accelerate it downward. And I'm not saying like you have to be dramatic in this, okay? Just a simple acceleration upward, simple acceleration downward. Keep in mind you're measuring the applied force, okay? Then you're going to try and move it up at a constant velocity, and then you're going to try and move it down at a constant velocity. So you're going to have 4 different readings. Accelerated upward, accelerated downward, up at as best you can a constant velocity, and down as best you can at a constant velocity, and get an idea of what those recordings are. So, you can hand out lab.
Yes, we green.
I think I asked for this last time. What the freak, Mr. Burkett?
green. I'm guessing the color could.
This is multiple days, right?
Why are we reading the book?
Yeah. You didn't put mine
It's
back.
multiple days.
Oh,
Okay,
wait.
so,
What page?
What buzzer?
I think
Huh?
we wasted a page.
I know, it's screwed up, it didn't.
That
It's
hill
supposed to
tree,
run
that was
front
a
and
whole
back.
tree.
Killing a tree, man.
So, here's where you're gonna record your four values. Up at a constant velocity, down at a constant velocity, accelerating upward, accelerating downward, okay? So as you go through this, and you begin to answer these questions, you have to understand what you're talking about. You're talking about net force, applied force, opposing force. And in this lab, anything going up is positive, anything going down is going to be negative. So in terms of data, that's all the data that you need for beginning of lab. Now, when you get down to, like, let's say, for example, number 7, I tell you, in the space to the left, not on another sheet of paper, off to the left, sketch and label. This does not have to be to scale. Sketch and label. All the forces acting on the mass while it was being accelerated upward. Okay? So, why are you folding my lab?
This is the wasted paper.
Okay. Why is it, what do you mean wasted paper?
The paper in the back.
Yeah,
Oh,
has nothing.
That's so
Making a paper.
weird. Okay, anyway,
Start.
that is odd.
Okay.
So, there's like 3 different ones on the front page where you need to sketch a free body diagram of what's going to happen. Do these right here, do not make it complicated, they're sketches. They're just gonna be off to the side. They do not have to be to scale. When you get to question number 12, okay, here's the basic idea on question number 12. Is that here's the elevator. And if you're an engineer, you always plan for a worst case scenario. So you're designing this elevator and you have to have, and you know the strength of the cable. So every cable, chain, whatever, has a breaking point. That's why this string has a relatively low breaking point. That's what I was able to pull it apart with my hands. So you know that a cable is going to snap if the force on it exceeds 2.96 times 10 to the 4th newton, okay? So that upward force can at most be 2.6 times 10 to the 4th newtons. So worst case scenario, this elevator is going to be at a hotel, and worst case scenario, 20 drunk frat guys decide, hey, let's see how many of us we can fit inside the elevator, okay? So you've got 20 people inside the elevator. The elevator itself has a mass of 500 kilograms. So what you're trying to figure out is the maximum acceleration I can make this thing have without snapping the cable. Oddly enough, you're going to start with the idea that force net equals force applied plus. Now, what's creating the opposing force? Gravity. You have to pay the gravity mafia. So the total, this mass is going to be the total mass of the elevator and the 20 fraternity guys inside of it. Okay? So that's going to be total mass. I've given you the applied force, so then you can find the net force. Once you know the net force, then you can find your acceleration. Okay? On page 2, you've got a helicopter. Okay? So you have 2 different situations. One in which the helicopter is accelerating upward, the next one where the helicopter is accelerating downward. Both at 1.2 meters per second squared. Which answer do you think is going to be bigger? The acceleration upward or the acceleration downward?
Downward. Word? Did it crash and burn?
I think upward, yeah.
Upward then.
Yeah. Okay, when you get to 15 and 16, This is going back to the limb lab. It's the exact same parameters. You have a mass of 5,000 kilograms, G is negative 1.67. You're gonna find the net force and the applied force once on the earth and once on the moon, and then you're going to compare those answers, okay? Remember, at the end of the day, how do you calculate net force?
Mass times acceleration.
Mass times acceleration. Keep that in mind. All right, when you get to page 3, we're gonna have what's known as an outward machine. So let me give you a simple example. Kevin, can you spin that around so we can get to it? Okay, so y'all have seen this before, right?
Yeah.
See,
So I've got a 500 gram mass on this side. I've got the stapler on this side. So clearly, which one weighs more?
500.
weight.
500 gram mass does.
Half a kilo.
So what's making the system move?
Gravity.
Gravity, right? Gravity is making the system move.
right?
So if gravity is making the system move, why isn't the acceleration 9.8 meters per second squared?
Tension, strength.
What about it?
There's a force applied.
Because the stapler is
Because
also acting downward on it.
Okay.
I don't.
So do you think maybe we can explain this in terms of force net equals force applied plus force opposing?
Yes.
C.
Let's kind of go with that, right?
So
So let's just focus on the 500 gram mass, okay? Don't worry about the stapler. What does a 500 gram mass weigh?
0.5 kilo.
4.9?
4.9.
4.9.
0.5 times 9.8 is 4.9. So if I just cut the string, what's the value of the force acting on a 500 gram mass?
Negative 4.9.
Negative 4.9 newtons. If I take negative 4.9 newtons and divide that by the mass of 0.5 kilograms, I'm going to get an acceleration of
Negative
Mm,
9.8.
yeah.
negative 9.8 meters per second squared, right?
Yeah.
Boom, there's a slope of my velocity. Cool. Now, obviously, my acceleration is not 9.8 meters per second squared. So is gravity still pulling down with the same amount of force?
Yes.
Yes. Everybody get that?
Yes.
That's still pulling down with the same amount of force. So since it's not accelerating at 9.8 meters per second squared, what does that mean in terms of forces?
There's another force.
There's another force acting which way?
The opposite.
Up it,
Yeah.
right? So, which one's bigger? The downward, in terms of the stapler. Excuse me, in terms of the mass. Don't worry about the stapler. Which one's bigger?
Down.
The
Gravity.
downward force or the upward force?
Downward.
Down. You think it's bigger by a lot?
Yeah.
No.
Not really.
Yeah, because not really. Okay, that's a relatively small acceleration. So you can look at this oddly enough in terms of force net equals force applied plus force opposing. So on terms of this, the applied force going up is going to be a little bit less than the downward force pulling up. Okay? Cool with that? And that's how I get a negative acceleration. Now, in terms of the stapler, is gravity pulling down?
Yes.
Gravity's pulling down on the stapler.
Yeah.
Is there tension in the string going up?
Yeah.
Which one's bigger? The
The
tension
tension.
in the string going up or the
Tension.
downward pull of gravity?
Tension up.
Tension.
Tension up. A little bit bigger, right? Now, here's what's important. Do you think both of these, the stapler, and don't worry about sign, I'm just talking the numeric value. Do you think the stapler and the mass have the same acceleration?
Yes.
Yes, but
That would make
Opposites are
sense.
connected.
That would
Yeah.
make sense, right?
Yeah.
They're connected, right? One can't fall faster than the other one
Yeah.
does. They have the same acceleration. Cool. So, the tension going up here is a little bit less than the gravitational pull pulling down. The tension here is a little bit bigger than the weight of the staple. So, here's what we're gonna do. The tension is the same throughout the string, okay? Because it's just one big long string. So we'll always assume that the tension in the string is the same unless you're told differently. So the tension in the string basically cancels out because it's the same throughout the entire thing. So what we're gonna do is we're gonna look at this in terms of, oddly enough, force applied plus force opposing equals net force net. So we're gonna, since it's moving downward, we're gonna make this be the applied force, okay? So this is important. The weight that falls is the applied force. The one that goes up is the opposing force. So I've got some positive applied force, 4.9 newtons. The weight of this, let's say, is 4.6 newtons. So if this weighs 4.9 and this weighs 4.6, I got an applied force of positive 4.9. I have a negative force of 4.6. So what's going to be my net force?
0.3.
0.3. Cool. Now I want to calculate my acceleration. So now I have my net force, 0.3 newtons. Do I divide by the 500 gram mass? Do I divide by the mass of the stapler? Or do I divide by the combined mass of the system?
Combined mass.
Always, always, always divide by the combined mass of the system. Okay? There's no exceptions whatsoever. You always divide by the combined mass of the system. Because what's happening is this 500 gram mass wants to remain at rest. The stapler wants to remain at rest. Both of them have inertia. They're both resisting a change in the velocity. Now, another way that you can view this, okay, so they're going to have the same acceleration. Imagine that I taped the two together and I applied a net force of 0.3 newtons to the combined mass. That would have the exact same acceleration, a 0.3 newton force, applied to both of these, would look the exact same in terms of acceleration as a 4.9, 4.6 acting on both masses. So both masses have inertia. Both masses are affected by the same net force. Both resist the acceleration because both of them have mass. Okay? Cool. Got it? Great. Okay. Give that a spin. Now we're going way over here. Okay. So over here on page 3. Right? So you're going to take a like so. A pulley. So basically we're going to build an outward machine. And you take a length of string like so. Through Vanessa. Very long.
Can't believe you.
So we got the string like this, and then we're going to have that suspended over the edge of the table. So initially, I'm going to put a 200 gram mass on both sides. So a 200 gram mass on both sides. What's going to happen? Absolutely nothing is going to happen. I will have no acceleration. Why? There's two reasons I don't have an acceleration. Either there's no forces at all acting on the system, or all the forces add up to equal to 0.
Add up to 0.
Yeah, there's a whole bunch of forces. I got 200 gram mass, 1.96 newtons. So I got 1.96 newtons of force acting on both of them. I've got the tension in the string acting up. They're pulling down on the cable. The cable is being lifted up and supported by the hook. There are heaps and heaps of forces taking place on the system. But at this point, they all add up to
0.
0. Now, I'm gonna take a 20-gram mass, and I'm gonna put that on one side, okay? So I'm gonna put a 20-gram mass on one side, and you can hook this up. We've got like these cute little hooks at the bottom. Okay? So now when I let go of it, what's gonna happen?
That one's gonna fall.
Ooh.
Okay? Does it accelerate?
Yes.
So why does it accelerate?
Because the forces don't add up to zero.
Force on it.
Okay, what do the forces not add up to?
Zero.
Zero. So is the 220, is this gonna be my applied force or my opposing force?
Apply.
Applied. So on this column down here, where it says the 200 and 220, your applied force is gonna be the 220 grams converted into,
2 grams.
multiplied by,
9 point.
there's gonna be your applied force.
Whoa.
So we're gonna make the opposing force be the 200. So clearly, which one's bigger, the 220 or the 200?
220.
220. Now, so the difference between those two is gonna get you your
Force net.
force net. Then to get a theoretical acceleration, you're gonna take the net force, or you're gonna divide the net force by 200 by 220, or the combined mass of 420.
Combined mass of 420.
Combined mass of 420, because you always divide by the total mass of the system, okay? So I'm here, I let go, boom, it's gonna fall. Now, that's gonna get you a theoretical acceleration. We also need to calculate an experimental acceleration. So this is where you have to decide what you wanna do. So if you're clever, and you are, what are you gonna let the initial velocity of the system equal?
0.
0. So once it begins to fall, what are some things that you could measure? You can measure distance, okay?
Time.
You can either measure how far the bottom one goes up, or you can measure
Time.
how far the bottom one or the top one goes down, okay? Pick one, I don't care, okay? Pick one. What else can you measure?
Time.
Time. So you can, again, I don't care which point you pick, okay? Now, this is where it's gonna get tricky as far as what you do in terms of measuring the time. If you're measuring the time, don't stand up here and try and guess when it crosses like a mark on the meter stick. You need to put a meter stick somewhere, okay? This is what you all have to decide. But if you're gonna do the timing, you need to get where you can get at eye level where it's gonna cross that mark. If you wanna pull it all the way down to the ground, okay, like that, and then let go of it, cool, you can do that. I don't care what the distance is, you all are big science people, you can figure it out. But just be consistent, and I have at least 2 people timing each trial. So, you're gonna have a distance, I don't care what the distance is, pick one, okay, pick a distance. You're gonna measure the time, you're gonna do 5 trials. Then, you're gonna take a second 20-gram mass, which I don't have, so I'm gonna put a 50 on here, you'll get the idea. So now I'm gonna put a 50-gram mass on here. So what have I done to my applied force?
Increase it.
Made it bigger. But what have I also done to the entire mass of the system?
Made it bigger.
Made it bigger. So what have I done to the entire inertia of the system? Made it bigger, right? So I do have a bigger applied force, but I also have more mass. So if you all visualize, if you can remember what the acceleration was when I had that 220, now when I let go of this thing, what do you notice about the acceleration?
Larger.
It's bigger.
Mm-hmm.
We do have a bigger applied force. We do have more mass, but that increase in force applied compensated for, more than compensated for the increase in mass of the system, okay? So here's what you've got. You're gonna do a total of 5 trials with 200 and the 220. 5 more trials with 200 and the 240. So, mathematically, give that a spin one more time. You're gonna let the initial velocity be equal to 0. You're gonna know some distance, okay? 0.4, 0.3, whatever you want it to be, okay? I'd go at least 0.3. Then you can measure the time. So what kinematic equation relates initial velocity, distance, time, so that you can find an acceleration?
X equals 1/2 AT squared.
C.
You're clever. What did you let the initial velocity equal?
0, is it?
0. Okay? 0. So, this is going to get you the experimental acceleration. Show your calculations. And by the way, this is not showing your calculations. 2x over t squared equals a. That is not showing you calculation. You wrote down a formula. Okay? That is not showing calculations. You have so here's the story for today. Get the data. Then start doing the analysis. Now,
Yes.
okay. So tomorrow, we'll finish the lab. You're also going to have a short quiz tomorrow. Okay? I emphasize short. It's going to be over the basic idea of forces, net forces, use of coefficient of friction, that type of thing. This is in no way, shape, or form a big blown hay test like we've had. This is a relatively short quiz that says, hey, do you understand where we're at with forces? Net force, applied force, opposing force, the use of coefficient of friction, when it accelerates.